My guest today is Professor Matthias Kling, who is Professor of Photon Science and Applied Physics at Stanford University and the Director of the Science, Research and Development Division at the Linac Coherent Light Source, LCLS, at the SLAC National Accelerator Laboratory. Welcome, Matthias.
Thank you, Gill. It's a pleasure.
Yeah, so thanks for doing this. So you guys had some great news last week or a couple of weeks ago. And I want to get a little bit of a historical perspective here. So SLAC stands for Stanford Linear Accelerator Center. Is that right?
Yeah, that's right. And it's actually started out in the 60s with an accelerator laboratory that at the time collided particles. So it was a particle physics laboratory. And for this, they had built a very long accelerator that then sort of, at the end, featured a couple of experiments where these collisions were studied. And sort of a version of what now is known to many people as LHC and CERN, what CERN is doing. SLAC actually stopped doing this kind of research experimentally a while ago, and that long tunnel that has been used for the original accelerator has been repurposed. So this is essentially what made room and enables the installation of LCLS. In fact, it's all based on an accelerator that brings electrons to nearly the speed of light and then makes them wiggle through an undulator. What's called undulators. Essentially, you have magnets that are alternatingly poled, and the electrons go through this alternating magnetic structure, and it makes the electrons wiggle, so they start to oscillate. And as they start to oscillate, they emit radiation, and that's the process that leads to the free electron laser radiation. The X-ray pulses that in the end we use at LCLS and now with LCLS2. And since you talked about this big announcement, let me maybe start there. So this is a once in a generation type of event that happened just last week, where essentially we inaugurated a facility that now has many orders of magnitude higher brilliance and in X-ray light than before. And typically in physics, you can hope to achieve maybe a factor of 2 or 4, or if you're very lucky, an order of magnitude improvement over some parameters that have existed before. Think about Moore's law, for instance, where the speed of processors is every 2 years or so doubles. Here, we're talking about a very different type of achievement. So in 2009, the first free electron laser in the hard X-ray regime with LCLS1 was inaugurated, which actually went billions of times over the brilliance of previous light sources, the synchrotrons at the time. And then with LCLS2, we again have a factor of 10 to the 4. That we are above essentially the limit that we had with LCLS1. And why is that important? Well, in the simplest explanation,
sorry, Matthias, sorry to interrupt. So before we get the details of it, I just want to get a sort of a general context. So, we have accelerators. Maybe general public knows, the Fermi in Illinois and LHC in Geneva, and there was a failed attempt underneath Dallas-Fort Worth. They all appear to be sort of circular in their construction, right? So, but a SLAC is a linear accelerator. So, was there any advantage in the initial going? Was it just simplicity of construction that in 1960s that SLAC was actually a linear one?
So to some extent, I think the point of having a synchrotron being circular is that as you force the electrons in these circles, they emit radiation because you're essentially bending their trajectory, and that leads to them emitting radiation. So they lose a little bit of energy, which means that you need to post-accelerate them again, and you can do that in a circular sort of structure the best way, and essentially keep the electron sort of bunches that run around the circular structure intact and always bring them up to a similar speed and refill them as you have losses. So in a linear structure, that is not possible, but it is possible essentially without losses to just keep accelerating these electrons to their highest possible energies. And essentially that is where linear accelerators have an advantage. So you can just speed up these electrons within a very sort of limited space in some sense to very high energies. And that is in the giga electron volt range. If you compare, for instance, what thermal energy is, so the room temperature that we're used to, that is about 300 milli electron volts. So it's much, much less than giga electron volts, which is 10 to the 9 electron volts. So it's many, many orders of magnitude above that. So these are very, very fast particles. Linear accelerators enable us to get them to that speed. And I have to say, one of the key aspects, I think, in that is important to us is how well defined that electron beam is. So it has a certain velocity in one direction, but we want it to be very confined and have as little sort of velocities into other dimensions. And that is still an area of research, but tremendous progress has been made on the accelerator technology side. And I'm not an expert on that, but I have to say, but that has enabled now with the superconducting accelerators that we also use for LCLS2 to essentially achieve very high, we call that quasi CW. So it's essentially a light source that emits flashes of light, but at very high repetition rates. So this light source that we had before, LCLS1, was 100 hertz, so 100 pulses, actually 120 to be exact, pulses per second. And we could irradiate molecules and look at their sort of, as they did their business. So we could look at their motions and study things in time and assemble movies of what was going on. Now we'll talk about that a bit more. Now with LCLS2, we have essentially 1 megahertz, so it's 10 to the 6 photons per light flashes per second, and that's so much brighter and so many more opportunities to essentially collect these molecules as they undergo motion, as dynamics is happening in these systems. And I'm just talking about molecules as an example here. That we get much better movies essentially of the dynamics.
So the accelerator, if I understand this correctly, Matthias, is in the business of smashing particles together and looking for something that comes out of it. And SLAC, as you say, is sort of repurposed for something a little different, right? So the news piece that you had sent me, it says here, SLAC fires up the world's most powerful Xray laser, LCLS2, ushers in a new era of science. And as you say here, with up to 1 million Xray flashes per second, 8,000 times more than its predecessor, it transforms the ability of scientists to explore atomic scale ultrafast phenomena that are key to broad range of applications, from quantum materials to clean energy technologies and medicine. And so essentially now you have LCLS1 and LCLS2, two instruments to look into, if I understand this correctly, to look into things that are really, really small and to understand their dynamic. So even things like chemical reactions and things like that. So I don't know how you do that. So before we get there, so the Xray flashes. The very large number of flashes, 1 million Xray flashes per second. So how do you create this Xray flashes, number one? And number two, just because the frequency is very high, what's the advantage of that?
Right. So yeah, let me first get into why flashes are interesting. First of all, if you have a flash of light, you can of course pack more sort of light into that one flash, and then sort of taking a bird's eye view on this. If you imagine yourself in a dark room, sort of sort of, let's say, a disco or so where it's dark, but then you have this disco light flashing at people, right? You can see them sort of frozen in their dance moves.
Yeah.
And essentially, the more light flashes you have, the sort of smoother becomes that motion that you're observing. And essentially, that is something that we're doing with the X-ray flashes of light as well. So we're illuminating molecules or quantum materials or biological specimen, and there we set something in motion in these systems by, for instance, exciting them into a, let's say, in a quantum material, if we can excite an exotic state in there that we want to use for modern electronics, then we can study, okay, how does that state behave? What happens after that excitation? How is, for instance, in biological specimen, how is sunlight converted into energy? And how, for instance, does the protection of the UV protection of the skin work, right? So we have, there's molecules that essentially convert that UV light into very fast motion of molecules without breaking the molecule, and that's a very important photoprotection mechanism in biology, and we want to understand how that exactly works. And so what we can do is we can use these light flashes to essentially take snapshots of that motion, and we do that, we repeat that, we do that many times, and actually change the time at which we irradiate the system with this light flash. And then if you put all of that together, you can create the movie of what goes on. So essentially we have a starting point where that motion kicks in, and then we can put all these X-ray images together into a movie. And the fine detail at which we can look at with that movie depends very much on essentially the brightness of the light source, its repetition rate, in fact, is an important parameter because it allows us to just get enough statistics and get enough data to look at fine details and not just very large effects. And another important point is these light flashes are very, very brief in time. So again, drawing the analogy to dance moves, yeah, that you where you use that sort of stroboscopic light to irradiate. Here, so if in that scenario you make the light flash longer, then you start seeing a smearing out of motion. So it's not really a frozen motions that you can put together, but you see some smearing. And essentially we need that light flash to be shorter than the dynamics that's going on. Or drawing the analogy to photography, if you want to photograph, let's say, a runner as the runner is running around the track, and you want to keep make a still frame picture of that runner, you have to use an exposure time that is short enough.
Yeah.
Because if you don't, then that gets blurred out, right? There's a picture that I like to show in talks of a tennis player, and what you can see is that the person is actually frozen in that picture, but the tennis ball that is very fast is blurred out. So that's just essentially an exposure time where the slow motion was captured, but the fast motion not yet. And we see that in the dynamics of these really, really small systems in the microcosm as well. There are things that are moving a little bit slower, and that's typically all the heavy things in nature, such as the nuclei in molecules or the lattice in crystals. And there's things that move really, really fast, and that's the tiny electrons that make up for the bonding in molecules, and they move on a time scale that's unimaginably short. Namely, it is on an attosecond time scale. An attosecond is 10 to the minus 18 seconds. It's a billionth of a second, and it's the best way to explain it, I think, is an attosecond compares to a second as a second to the age of the universe. So
Right.
it's an incredibly short time scale, but that is the natural time scale on which electrons move. And we're now able with LCLS, thanks to a very strong team here that has developed these capabilities, we're able to produce these attosecond light flashes with a free electron laser. And actually at the moment, it's the only one in the world that can do this. And that enables us to look not just at, and I will come to the resolution as well, but it enables us to sort of capture motion all the way from that very, very fast motion to motion that, of course, extends into longer time scales. So if you can capture the fastest motion, there's no problem in capturing also slower motion.
Yeah, so I get the intuition of this. So the dance floor is actually a good analog to it. So yeah, so when you have a lot more light flashes, you get better and better resolution or better and better picture of what's going on the dance floor.
Right. Imagine
And
you have
yeah,
two situations, two moves, right? And you see the person doing this, and then in the next moment doing that.
right.
In order to understand how you moved from this situation to that situation, you would need all the pictures in between, right?
Yeah.
Because you can't tell if I moved my hands sort of left or right just from looking at these two. And that's essentially what we see in the microscopic world as well. If we take enough time steps, we can see what we call intermediate states. So we can see how the system evolved from A to B to C to D. And that is very important because well, for two reasons. One is because we want to understand these systems on a very fundamental level, being able to also tweak essentially theoretical models to predict this behavior. And that will help us to use the theoretical models for predicting new systems that we haven't done experiments on. And the other is that there is new functionality that comes from the time axis. So if you imagine you have, for instance, talking about medical applications, if you have a new drug that has certain, it's essentially a large molecule that enables you to fulfill certain medical functionality. If that changes its configuration to fulfill that sort of function, then you can think of it as, okay, it's initially in one configuration and finally in another, but there are many sort of intermediate steps in between. And these intermediate steps, understanding them will enable us to potentially use one of those intermediate steps for additional functionality that hasn't been exploited at all so far. So we might be able to optimize the use of chemicals, of drugs for other purposes, looking at essentially the sort of intermediate steps. I can give you one more example maybe that I'm very excited about, if I may.
Yeah.
The
Look, I just want to ask you a clarification question. So on the dance floor, you are still limited by the eye's ability, the eye's shutter speed. So you have to really sort of increase the frequency to some level that it is going to look continuous to the eye. Here, you don't have any such issue. So you're going to take 1 million pictures a second on a chemical reaction, and then you can put that all together, exposed into a movie, right?
It's slightly different. So
Yeah.
you're right about that analogy. So that's the way it would work. But here we essentially, what we do is we can use an arbitrary time step, let's say, from the initiation of an event. So that's the person that starts dancing, right? And where you take that picture. And let's say that dance is always exactly the same. Yeah. So no change, always exactly the same. So you can reproduce this a trillion times. Then in principle, we're not limited, of course, to taking data for 1 second. We can take data for many hours, right? And then it's not 1 million images, but it's much more than that. And we can choose the time step. So we're not limited to taking essentially just 1 million images a second, but we can step very much in between in intervals that we define. So, and that's possible optically. We can define, as I said, attosecond intervals, which is many orders of magnitude below that. And then, however, let's say if you want to step through your process that is on a scale of, I'm just giving you an example, 100 attoseconds, really short time. So you need 10 steps to reach a femtosecond, and then you need to reach another, so many steps to reach with the same precision the next level, which is a picosecond. You will have to record a lot of images, and essentially at some point 1 second of data acquisition is not enough, even at 1 million shots per second. You will need to record for hours. But now imagine if you have a light source that has much lower sort of rate at which the light is flashing. You can still record the very same movie in principle, but you would need weeks, maybe months, to take the same type of data. And then it becomes impossible. So that's the main difference between having many pulses and few pulses. It enables us to all of a sudden record things that were impossible before because we just couldn't. I think typically an experiment that gives you reliable and good data that lasts for somewhere between hours and days, but that's about it, because also these light sources, we can use them in a sort of shift type fashion for typically something like 60 hours or so, and that's one experiment. And then within these 60 hours, we have to record all of the data that we're interested in. And of course, that involves also setting up for these experiments and making sure the parameters are right. So typically, the experimental data that is published includes a couple of hours of data collection. So, and that means if you have a very high repetition rate light source, you can take so much better quality data and so many more sort of time steps in between that you haven't seen before within these few hours that otherwise would have been impossible. So it's really it's a game changer in how we can look at the micro world.
It's mind-boggling. So we are up to a point that we can actually take pictures of chemical reactions. Essentially, we can see how atoms and molecules move around in very, very short periods of time, right?
Yeah, let me talk about that a bit, because you mentioned the wavelength axis as well, right? So why X-rays? What's so special about X-rays? Femtochemistry actually was honored with a Nobel Prize in, if I'm not mistaken, in 1999 or something like this for Ahmed Zewail. And he actually looked at chemical reactions on their natural timescale, so bonds forming, bonds breaking, and that is a femtosecond timescale. So this sort of ultra-fast chemistry did exist. However, what was not possible until recently, when these FELs came about, is to be able to look with essentially atomic precision. So X-rays are, it depends a bit on their energy range, what we can do with them, but at the slightly lower energy range, up to a few kilo electron volts, which we call soft X-rays. In these soft X-ray ranges, we can look at, we do spectroscopy, and the spectroscopy is very specific to atoms. So, for instance, a nitrogen atom in a molecule has a certain absorption edge, and that lies in the soft X-ray range. And then we can look at this edge and we see chemical shifts. So we see whenever the molecule is doing something different, that sort of electronic structure around the nitrogen atom is changing, and we see that in the signals. So we can essentially look at what happens in molecules, but with atomic resolution. So we can look at each of the atoms inside the molecule and see exactly what's happening. So we can, from that information, construct what you would call a molecular movie. So we directly get information in 4 dimensions. So it's 3 dimensions in space, and then the 1 dimension in time. And that's the spectroscopy aspect of it. And there's another very important aspect that is exploited at hard X-ray FELs, and that's related to diffraction. So what you can do is you can, for instance, diffract light from a lattice, and this has been exploited for many years at synchrotrons. And it gives you essentially information on the dimensions of in that crystal or in that material, and you will learn how the crystal structure, first of all, what it is exactly that you are looking at. So we can use that diffraction data to infer what the structure looked like at a certain moment in time. So we can follow that in time. But we can look at deformations of materials. We can look at dynamic processes where you start, for instance, let's say some kind of wave that goes through the material. We can study superconductivity, which actually is in principle a phenomena that's also related to often, certain modes in the material that we can observe in the deformation of the crystal, of the lattice, and things like that. So essentially, X-rays give us, first of all, atomic resolution spectral information, but they also give us that sort of spatial information if they're in the harder X-ray range. And we have, LCLS has 2 experimental areas. The first one, which we call, that comes after these undulators that create the X-rays, The first one, called the near experimental Hall, actually does most of the spectroscopy part because it's using soft X-rays, and then we have a far Hall that is using the hard X-rays.
Yes, I want to understand that a little bit, Matthias. So could you talk a bit about the engineering around this? So more generally, how do you produce this X-ray flashes? What is sort of the mechanics underneath that?
Right, the mechanics, yeah, it's actually quite impressive. I recommend everyone that's watching this, if you find the time, come and visit us and go on a tour. There is initially, as I said, actually, I didn't say that yet, but the whole accelerator is about, the tunnel is about 3 miles long, and at the moment, each of our facilities occupies about 1 mile of that long tunnel. But that just creates these very fast electrons. And then these fast electrons are sent into that sort of magnetic structure, the undulators that have opposing, alternating magnetic structure.
Sort of wiggling the electrons as they move through. That's the
wiggling motion, right? And these magnets are they're very strong. They essentially are held back by it's engineering wise, it's very impressive because they would essentially, if you wouldn't hold them back by strong enough forces, they would just smash into each other, right? Because these are they're attracting magnets, and there's a strong field, and if you don't do anything to sort of hold them back actively, and then we can control these massive undulator structures that have a lot of weight that they're moving. We can control them to a very fine precision. So what we control is the gap between the magnets, which in the end is controlling the field, and with the field we can control the excursion of the electrons, and as the excursion is controlled, we're controlling the X-ray wavelengths that is produced. So we have very fine control over which wavelengths we're producing. These are called variable gap undulators. So we are able to move them, and that enables us, with the exact same electron beam that comes in, to produce different types of X-rays that come out.
So that's what you call the undulator. So it's essentially making the free electrons move in some fashion, and that movement creates the X-rays.
Right.
And then you have to direct those X-rays to some systematic position, right, to use it. So what's on the back end of that? Yeah.
Right. We dump the electrons. And then the X-rays, so light actually prefers to just go in a straight line. And X-rays in particular, because they're, as people know, they're penetrating through a lot of materials easily, and it's very difficult even to bend them. So we have to go through quite some efforts to bend them in their path and to focus them into an experimental chamber. But we do that. So imagine from where the undulators are, we essentially just go in a straight line and then into what we call the experimental hutches. And an experimental hutch is essentially an experimental infrastructure that serves a certain purpose. So we have an experimental hutch that deals with atomic and molecular and optical physics. We have a hutch that deals with, for instance, chemical dynamics, and then we have instruments and other hutches that look at materials and things like that. And it is important to have this sort of instruments that are very specific to a certain area, because what we want is on that instrument to have enough capability to inject the targets into the X-ray beam, to manipulate them, to maybe cool them down to very low temperatures, as in quantum materials, you might want to cool them down, to change their angles with respect to the X-rays and all these kinds of things, and then have various monitors to look at what comes out of the experiment. I haven't talked about that much yet, but the sort of simplest thing you can do is just look at whatever X-ray light is transmitted through your sample or reflected from the sample. That's a sort of X-ray in, X-ray out kind of experiment. But often we actually look at other particles, such as X-rays create electrons, or X-rays create ions, charged ions, or something else, and essentially have detectors that detect these observables that are produced in an experiment.
So that's where the cryogenic cooling is applied. I know that you had to cool these things down to 2 degree Kelvin or something like that.
Yeah, that's the accelerator. So in fact,
okay.
the cooling down the accelerator helps us to just operate at much higher rates. So the main advance between LCLS1 and LCLS2 was to go from normal conducting to superconducting accelerators, and essentially that enabled us to run them at much higher current, so much higher repetition rate, without the structures melting, right? So because that would happen otherwise, you just produce too much heat. But in superconducting materials, there's no resistance, so we can crank up the power while essentially not producing any heat and or not much heat. And I think this is the trick. So at the moment, the accelerator LCLS2 is using superconducting technology at 2 Kelvin, which is actually colder than outer space. So it's really very cold. Very cool. But then the rest of what comes after, the undulators, the experimental halls where we do the experiments with these X-rays, they typically don't use cryocooling. There is one exception, and that is in materials research. When you look at, for instance, superconductivity in materials and you study it. So on the one hand, we use it for the accelerator for making the X-rays, but then in studying materials, sometimes we actually cool them down on purpose, also to very low temperatures. Not necessarily 2 Kelvin, but let's say 10 to 15 Kelvin or so, to look at how superconductivity forms, how it interacts with other types of excitations in the material, and to essentially, let me bring it to one point, to develop the next generation superconductors. Right? And that's important because imagine we would live in a world where electricity is transported from where it's produced to us to the users by superconducting wires. Then in principle there's zero loss along the way. So we would have a much more efficient way of distributing power. We would need to live with much less power produced because the losses are not there. And it goes on and on. I mean, we could make cars more efficient. We could make everything more efficient, essentially, if we would have, and that's the point, if we would have superconductors that work at higher temperature. At the moment, we have to cool most of them down to very, very low temperatures. But it's still a dream of the science community to develop other materials. And we're contributing to that effort. It's not all we do a lot more, but that's part of the research that's being done.
Yeah, I mean, I kind of looked into this, Matthias. So there was some news from South Korea that they found a room temperature superconductivity superconductor. Where do we stand on that? Has that been replicated?
Well, I'm not an expert on this. I think the rumors that I have heard is that there are some doubts on this result, and I think any news like this where, for instance, room temperature superconductors are postulated, they need to be verified by the scientific community. So as a professor and researcher, I really truly believe in research being sort of a mission of humanity where, yes, it's important to make discoveries, but it's just as important to reproduce them and to be able to reproduce them. So if you hear news like this from any lab and it can't be reproduced, that is a problem. And I've not heard about anyone else reproducing this result yet. So
yeah. So I would think that the answer to this question is no, but I'm going to ask this anyway, Matthias. So we have this wave function collapse problem in quantum mechanics. Maybe LCLS2 doesn't get there. Maybe there's an LCLS3 get there. Can we actually practically look at if this is actually true? that when you observe the wave function collapses explanation?
So, yeah, I've taught quantum mechanics, so I know a little bit about that, but I'm not sure I understand your question correctly, but let me answer what I understood. So we do look at quantum effects. In fact, the X-ray light that we use essentially often interacts with materials in a quantum way. So it's an X-ray. We call these light particles photons, and they have a certain energy that depends on the wavelength, right? So then essentially we have such a photon interact with the material that creates an electron of a defined energy and an excitation in the material of a defined energy and so on. So these are all quantized effects. So we do look at quantum effects all the time. And what enables us to do so is essentially using the quantum nature of light. So in that aspect, we are able to look at also quantum effects, for instance, in molecules, where initially we have so what you can have in quantum mechanics is essentially you can have similar to Schrödinger's cat, you can have a molecule that exists in sort of two states at the same time, and it doesn't quite decide which state it actually, and it ends up in until you do the measurement. And then the measurement actually collapses the wave function, and it will tell you whether you are in state A or B, right? And there's a certain probability that is given then by the laws of quantum mechanics, how often you end up in state A or state B. But before we do the measurement, the system exists in this, it's called coherent superposition of two states. We have that very often. Actually, it's a beauty of quantum mechanics, and it's also what is underlying quantum computing, that you can have essentially a superposition of states. And so that the sort of collapse of the wave function is what we induce in measurements intentionally to get a certain result. But since quantum mechanics is deals with probabilities, just observing that once means nothing. So you need to observe it many times and then measure essentially the likelihood you end up in a certain sort of final state, and that will tell you something about the quantum system in the end.
Right. Yeah. So we have a lot of life sciences folks listening to this, Matthias, and so this is going to really push into life sciences research a little bit, right? So chirality is a big issue there. Some chemicals are toxic, some chemicals are beneficial. So how would LCLS2 impact that arena?
Right. I think in many ways. So the first one is that essentially we're now able to look at the functions of enzymes, and I should always say that we really means not us here at the facility, but the scientific user community that comes to us and is using the facility. That's a very important point, right? So it's not just a few people that sit here at SLAC that come up with all the ideas. Hopefully some of the ideas, but it's really it's the scientific community at large, so the global community that comes up with the best ideas. And among these ideas are groups that study the functionality of enzymes, and as an example that is somewhat related to biomolecules, not necessarily to health yet, is we can use these enzymes for producing clean energy, for decarbonizing the atmosphere and things like that. So using biological specimen for new sort of functionality that helps humanity to deal with important questions of sustainability is something that we're heavily invested in, and we see more and more at the facility. And another one I think that relates a bit more to what you were asking is how can we essentially design systems to have new functionalities? So to, for instance, open new ways to treat diseases, or to protect us from harmful radiation or things like that. And this is research that we have been doing to, I think, some parts with LCLS1, but the main issue was that we essentially were limited in two things. We were limited at sort of how well we could resolve these dynamics, because we're talking about large molecules typically in biology. So that means you have a very sort of complex structure to solve. So you need a lot of data to do so. And then being able to to look at the dynamics or the time axis will be impactful. Another thing is often when structures are investigated of viruses or of some specimen we're interested in, such as there were also studies on the coronavirus at LCLS. Let's say in conventional studies, what actually happens is, they need to be crystallized in large crystals. And then you can go to a synchrotron and you can rotate the crystal in the beam and you can take that sort of data that tells you something about the structure. And often we actually don't know the structure. So knowing the structure helps a lot in order to understand what their functionality is. Now with LCLS, the advantage is we have so much light within that one burst that we can essentially, we don't need to rotate the crystals anymore. We can just take data on a single very, very small crystal, or not even a crystal, just on the molecule itself, and record that within one single image, one shot essentially of this high repetition rate source, and then do that at room temperature in conditions where actually that system functions in real life. So when you cool it down, you form a crystal and you have it at sort of these conditions where it's not natural in its environment. So most of the molecules in our body are in a water type environment, right? And we want to reproduce that. We want to create conditions that are very similar to what we see in nature. And I think that's what we're able to do at LCLS. We can look at systems in their sort of natural state and environment, and then resolve their structure, and their structure, of course, with time. But it's also it's important to be able to resolve their structure under these conditions.
Yeah. So if you were to summarize sort of the practical side of this, Matthias, so let me see if I understand this. So we can have a very detailed definition of materials, how they look, how they act, how they react, all that stuff. That information then allows us to potentially design custom materials, right? So that goes into superconductivity, that goes into life sciences and other areas. So foundationally, well, would I be correct if I saying the primary use of the technology is understand materials in a very detailed fashion, and then design materials for novel uses in a variety of areas? Would that be a correct summary?
I think that is a very good summary. There is a whole area that I did not yet mention. Of course, there is the discovery aspect also, right? So we might be. I'm very optimistic that we might be able to see materials in states that haven't even been discovered just yet.
Yeah.
But there's another aspect that we haven't talked about yet, and that is we can look at materials under very extreme conditions. So we can create conditions that we see in the inner sort of parts of of planets or the sun. We can go all the way up to conditions that we see there. And these are conditions we can actually create artificially using a very high intensity laser, not the X-rays, but an optical laser. And then, however, that sort of material in this state at very high temperatures, very high pressures, for instance, exists only for a very brief amount of time. So we can make it, but only for, let's say, a few hundreds of femtoseconds or whatever that is. And so we need then again these ultra-fast X-ray light flashes to look inside those materials at those conditions to understand what's going on. And I can give you a very nice example that I like from research that was done here, where a group looked at essentially water under very high pressure and high temperature conditions. And what they saw is that under these conditions, water becomes metallic. So it starts to conduct currents, and essentially it forms a new form of ice that wasn't discovered so far. So I learned being here that there are 19 forms of ice that actually have been discovered so far.
Yeah,
I would have thought there's just one, but no, there's many more. And this, in the end, is responsible, for instance, for the magnetic fields that form around the planet Neptune, and that has a lot of sort of water in its atmosphere, and essentially that if that becomes metallic, it fulfills a similar functionality as the iron core in our planet Earth. So this was measured before by probes that were sent to that planet, but it wasn't fully understood how that actually can work. And we can create conditions here in the lab that reproduce essentially the conditions, these very extreme conditions, and then learn something about them.
Yeah, that's so interesting. So all these exoplanets we are discovering, and we have some measurements of the conditions that exist there. And potentially, if those conditions can be replicated, maybe this type of experiments could give us some insights into the chemistry that might be there, potentially.
We're, for instance, learning about chemistry in outer space. We're doing experiments, or the experiments being done at LCLS as we speak, on what happens on icy dust particles in outer space, and how potentially molecules actually also form under these conditions. So yes, that's something that's being done. For the planets, I think the conditions I talked about are, of course, giant gas planets and things that wouldn't necessarily support life. But I think we learn a lot about the universe from light that we see from these planets, that we see from the stars. And in the case of planets, again, I'm not the expert, but there's certain sort of markers in the atmosphere of these planets that we can look for. And we do something very similar in a way at LCLS with X-ray spectroscopy. It's a very different spectral range typically than that, but we look at sort of fine details in how the environment is changing, which sort of molecules are forming. And in principle, if there would be an X-ray source on these planets, we would be in a good position to tell what's going on. It's typically these frequencies are in the infrared or even sort of microwave frequencies where interesting transitions in molecules happen in the atmosphere of exoplanets that are, let's say, would support life, and that that would potentially be interesting to us. But as a physicist, I think I always tend to strive for an as complete knowledge of the universe we live in. And that means if we can describe, all kinds of scenarios where you have these very extreme conditions we don't see on Earth, but we see in other planets, even in our own solar system, I think that is absolutely great. And that might enable us to use some of those conditions to artificially create, for instance, fusion, right? This was big news also this year, that breaking essentially the limit where laser-induced fusion can generate more power than was put in, and this is it's definitely a breakthrough that gives me hope that one day we might be able to recreate what the sun is doing every day to give us energy on Earth, to produce energy in a very sort of efficient but also much more environmentally friendly way.
Yeah. If we get fusion, we can suck all the carbon out of the atmosphere too. So it solves a lot of problems. So in conclusion, Matthias,
and in fact, we do have a program now at LCLS. It's very new, where we pay a bit more attention also to research that is important for the fusion community. And we can't just create exactly the conditions here, because we don't have these powerful lasers, but we can create conditions that are important for the furthering of these facilities. So it is research that in the end will contribute to making these facilities better and getting us one day to actually have a reactor that can be implemented. As you probably know, there are many companies out there now that are trying to achieve this goal.
Right. So in conclusion, Matthias, I mean, this is fantastic, fantastic instrument. I would imagine there is a line of people in Palo Alto trying to use it.
Yes.
So, so do you see sort of an LCLS 3 in the making? Not immediately, of course, but do you see we can go further?
Yeah, I like the question. So what we have actually planned next, and it's already it's a train that's moving at high speed, is to upgrade LCLS2 to LCLS2 HE, HE for high energy. LCLS2 at the moment, and we'll start using the first photons very soon, is producing soft Xrays, so the slightly lower energy Xrays, and we can use them for a lot of exciting experiments. But we also plan an upgrade that allows us to produce these hard Xrays that I explained we use for instance, imaging applications. That will happen in on a time frame of a few years, so we will have that upgrade. And then we have yet another upgrade where we will inaugurate or bring a petawatt laser system to LCLS to create even more extreme conditions to study these very extreme sort of conditions in materials. And there are many ideas how to exploit essentially the capabilities of the accelerator in a better way. So at the moment, we with the superconducting accelerator, we're so far above what we can even fully exploit experimentally. In principle, we would dream about a synchrotron-like farm of experiments that is fed by this accelerator and the X-rays that come out of it, and that's sort of going from just 2 undulators that we have now, so we can run 2 experiments essentially in parallel. We would like to go out to maybe 10, something like that, and we could operate them all at the same time. Imagine the scientific output would be tremendously higher. Would enable the community to come here more often, and the sort of it would become much easier to get access. And that's sort of what we have in mind for just exploiting LCLS2 in a full way. And there are plans for, or dreams about what the next facility, LCLS3 or LCLS something, some number, would look like. And it's, I think this is really, it's what I like about X-ray science with free electron lasers is we have a few partner facilities around the globe. They're all very excited about this because it's a very young field. I mean, the first hard X-ray FEL was LCLS and just started operation in 2009, so it's relatively young, right? And it's just the development is mind-blowing. I mean, that within just that very short time frame of something like now it's since its inauguration, it's 14 years. So in these 14 years, we see yet another orders of magnitude increase in performance. It's unbelievable, and I think it will keep going at some rate. That we still see sort of very novel concepts come to fruition, and where we have light sources that we didn't think were possible before. And in every of these steps, I mean, I'm excited about just the physics of these light sources, but there's also always science that is all of a sudden being enabled by having this one of these new tools with imagine if you have a microscope and you're looking at a small structure. You need light to resolve all of the details. So if you have just so much more light, it becomes much easier to look at finer and finer details. And as we go down and exploring finer details of the microcosm, we would like to have even brighter light sources. But I think for the time being, we have a lot to do at LCLS with LCLS2 starting operation with LCLS2 HE in the plans. But our imagination, of course, doesn't stop. So I can tell you. Yeah.
Yes. Sorry. So last question. So is the physics limit the temperature? How cold you can get?
Well, in some sense, because it's the sort of temperature of the electron beam that matters. I learned this from a colleague actually today. That the electrons, we want to accelerate them first of all to very high energies in one dimension, but we want the We call them electron bunches, so a couple of electrons that all sit together and that we accelerate in these structures. We want them to have as little temperature and other dimensions, because this is detrimental to the free electron laser, so the lasing process. And so in some sense, the electron beam being cold is important. We're working on improving on that. But I think I have to say, accelerator technology came a long way, and it's amazing where we are nowadays. We actually have to catch up in many other fields. We haven't talked about that yet, but for instance, we don't have X-ray imaging detectors that work at these very high rates. So we can, at the moment, these detectors, there are some developments here at SLAC, and we have seen the first chips produce more than 5 or kilohertz, which is encouraging. But now compare 5 kilohertz, 5,000 images that they can take per second to the 1 million we could potentially produce. Yeah. So there's a big gap in what we can produce in terms of the light source and what we would need on the experimental side. So we have a very active and vibrant research program on how do we deal with these detectors, how do we develop them, how do we deal with a large amount of data, for instance. You cannot imagine how much data we're producing. I mean, it's terabytes within just minutes, right? And if you run for a few hours, I mean, you have so much data. Essentially, we have to come up with new ways how to, compress that data, dig out the most important information really in real time, essentially, and just store what is important. And that's not an easy task, because obviously you're creating more and more data as you're processing it. So this has to be a supercomputer that essentially deals with this problem. And then we need storage. We need storage solutions for so much data. And luckily we're living in a world where computer technologies and data analysis and artificial intelligence and machine learning and all of that is really growing very strongly as well. And we're making good use of the developments in this community to help us essentially deal with this big data problem.
Excellent, Matthias. This is great. Thanks so much for spending time with me.
Yeah, it was a pleasure. Thank you, Gill.
Thank you.